Okay, I'm going to get started while Sandeep is setting up the camera. So, welcome to 677 Spring 2015. As you know, this class has two sections. Since all of you are here, you are in the in-class or the classroom section. There's also an online section where the classes are being recorded and the video is being provided, and those students are going to do all of the same work. So you will see that we will be recording all of the classes. Okay, so bear with us for all of that because it is necessary for the students who are enrolled in the online section of the class. All right. So what I'm going to do today is just give you all a quick introduction to the course, run through the syllabus, talk a little bit about what background is expected, what we are going to be doing in the class, and then in the last half an hour or so, we are going to go through a quick introduction to distributed systems. I'm going to define what they are, broadly talk about their benefits and so on. Okay, the first real class is going to start next time. Today is mostly an introductory class. Okay. There is also a sign-up sheet that is going around. This is meant for me to figure out how many of you have not registered and are on the override list and need to get into the class, and I need to figure out how many I can let in based on the enrollment. Okay, the class is pretty full, but there are just a couple of spots I can make some accommodations for. Okay, so if you're not on the registered list, you should put your name down. Okay, even otherwise you should, but specifically if you're not, and then come see me at the end of the class. Okay. So we'll start with the course syllabus. The TAs are not here today. I'm going to have him come and introduce himself next time, but my name is Prashant. So my office hours are going to be right after class on Mondays, and by appointment. If you have any questions, you can't come during office hours, send me mail, you can set up a time. Okay? The TA is also available to meet with you. His name is Pratik Sharma. As I said, I'm going to have him come next time and introduce himself so you know who he is. Okay? His office hours, I will send out an announcement. Okay? I don't have it yet, but I'm going to send that out. Okay? Course web page is here. Okay? All the course slides are going to be posted on the course web page. Okay, so you will, whatever I present here will be there. And since there's an online section, you also have the benefit of having the course lectures posted online as well. Don't use that as an excuse to not come to class. There are numerous benefits to coming to class and asking questions and whatnot. Okay. There is going to be a course mailing list I'm going to set up. You don't have to do anything. Spire will add you to it. I will periodically send out course announcements on the course mailing list. Okay. There is also a Moodle page for the course. You I presume all of you know what Moodle is. That's the course management system. All of your lab work, homeworks, you will turn in electronically. Okay? You don't need to turn any hard copies. You just turn it in. It's time stamped. It does not get lost. Okay, so we will just use Moodle for all of the course logistics. Okay, this is also useful for the online sections who don't have a classroom time for them to come and do anything. So we'll use Moodle for turning in labs and assignments and whatnot. Okay, so Moodle page is actually already set up, but it's blank at the moment. As soon as we have lectures, I'm going to go put the course slides, mirror the slides from the web page also to the Moodle page, okay, so that you can follow along on either of those two sites. Okay. Okay, so as far as the course outline is concerned, we are going to use a textbook, which is Distributed Systems by Tannenbaum. Okay, it's a somewhat old textbook, 5-6 years old now, so you probably can get a used copy for less cost, which is just as fine. I will keep one copy on reserve in the library. If you need to use the library copy, you don't wish to purchase one, that's also fine. I'll be handing course notes as well. Okay, this is the only book that we are going to use. As I said, it's somewhat dated. It doesn't have some of the more interesting newer material on cloud computing, virtualization. I will have handouts for those that I'll give. Okay, but if there's one book that you wish to have, this is the one. Okay, any questions about the book? Okay. So that's the book, and the course outlines follows roughly the chapters in the book. And I'm going to from time to time use material from the book, at other times use outside material, but the outline is actually based on the book. So today is going to be introduction. We just talk about distributed systems and whatnot. Okay, next time we're going to talk about architectures of distributed systems, client server, peer-to-peer, and those kinds of architectures. And the first major component of the class is going to be on communication in distributed systems. This is going to be dealing with RPCs, RMIs, message and stream-oriented communication. Okay, so this is how distributed systems or applications interact or communicate with one another. Okay, that's going to be the first component. Then we are going to talk about processes, threads, virtualization, process management. All of that is going to come next. Okay? So we are going to build up from where we will leave off in undergrad operating systems class and talk about things like process migration, how processes can be virtualized, what virtualization means. All of that is going to come under this topic of process management in distributed systems. Okay? We'll have a short overview of naming and name management in distributed systems. So this is the topic of you build a very large distributed systems. How do you address objects? How do you refer to them by the name? How names get resolved to where the objects reside. Okay? So that's going to be the topic of naming. And then we are going to spend a good bit of the class, maybe a good third of the class, talking about what I broadly refer to as canonical problems in distributed systems. Okay, so we will study these problems in the abstract, but these are all problems that will occur over and over again in a variety of distributed systems. Things, anything from time synchronization to distributed synchronization, lock management, a whole slew of topics that we are going to cover under this, and that's really the heart of what when you consider distributed computing. Okay, we are going to go through all of those. It's going to take us several lectures, and we'll study them in the abstract, but I'll give examples of real world systems that use these concepts, and in the lab we are going to use these concepts. We'll get a good feel for how these concepts allow you to solve real problems in real distributed systems. Okay, but so that's the canonical problems topic. And then we will have a series of advanced topics on replication and consistency, caching, how this can be used to optimize the performance of distributed systems. We'll talk about fault tolerance, how can you build design systems so that if some machines fail, other machines in the distributed systems can take over and allow you to continue operations without taking the system down. That's the topic of fault tolerance. I'll talk a little bit about security in distributed systems. Not a whole lot of detail there because there are other graduate level courses that deal with security, but we will talk a little bit about how security needs to be considered in distributed system design. And there will be one last topic on middleware systems. I'll talk about middleware today as well on sort of case studies on middleware systems. And time, as time permits, there are some advanced topics that I cover in some shape or form. Just depends on how much time is left towards the end of the course. The web part we always have time to cover. So I'll talk about web and how you can design systems using web and web services. We'll talk about cloud computing and green computing as well. Okay? And probably multimedia and mobile systems if we really have the time. That's really at the very end of the course. Okay? So that's an outline of what the course is about. Okay? So today we are just going to have an introduction, and if you don't understand what some of these things mean, that's okay. When we come to the topics, I will go into more detail of what these things mean. Okay? Any questions about this? Okay. So as far as some other course logistics are concerned, I already showed you the book, which is Distributed Systems by Tannenbaum. Okay, I don't make it a requirement, it's a recommended book, so feel free to buy it or not, depending on when you want to have a copy. Okay, now as far as grading is concerned, there is going to be some homeworks. Okay, there are going to be weekly quizzes, okay, on Moodle. This is actually mostly for the online section students so that they follow along, but you have to complete the quiz as well. So quiz is going to come out on Friday, is going to time out on Monday morning. Okay? Every week there's going to be a quiz based on the 2 lectures from that week. A very short quiz, not a whole lot of points. There's going to be no makeup for a quiz. So if you fall sick, you're traveling, you don't manage to turn in a quiz, don't worry about it. The aggregate grade that I assign to all of the quizzes is so small that missing a couple is not going to make any difference to your final grade. This is mostly meant for you to keep pace with the class and not just wait until an exam comes up to start reading up on the material, because you will see that we are going to cover material at a fair clip. Okay, so every 2 or 3 lectures we will finish a chapter. Okay, if you don't follow along, you will fall behind. So the quizzes are meant for you to keep up with whatever is going on in class. Okay, so homework is 15% of the grade. Class participation and these Moodle quizzes that I talked about, 5% class participation obviously applies only to the in-class section. Online section, there's no class, so there's no class participation there. Okay. 2 exams, midterm and a final, which is good 40% of the grade, 20% each. Midterm is going to be maybe a month and a half or so from now. I'll announce the date. Okay, that is going to be a closed book exam. The final exam is usually an open book take home exam. Okay, as always been the case, we are going to keep that same tradition. Okay, so 2 exams, midterm and a final, and a good part of the grade is going to be assigned to the lab part of the class, where you are going to do programming. Okay, you are going to program different distributed systems concepts, and each assignment is going to build on previous assignments. Okay, that's going to be 40% of the grade. Okay. So what that tells you, there are 2 things to keep in mind. First is you need to be familiar not familiar, you need to be good at programming in some high level language. The assignments don't specify any language, you are allowed to choose whatever language you want. Okay. Just as if you are given a task, typically you have to make all the design decisions, including what language to write it in and so on. So any language is okay, C++, Java, even Python, or some people have used obscure languages from time to time. Any of those is acceptable. You will obviously have to make that design decision and submit design docs and so on. Okay, so, but you need to be good at programming in some high level language. That's an important prereq for the class. Without that programming assignments part is going to be hard for people to complete. The second thing you need to know is, I assume that you have taken an undergrad class in OS. Okay, at one point that used to be a prereq for the class. Without an undergrad class, you couldn't even register. Right now, I don't enforce the prereq strongly, but it's a very strong recommendation that you know undergraduate concepts in operating system. You may ask, you have not taken such a class, what are you to do? I'm going to leave that to you to police. Okay? So if you have not taken a class, it's your responsibility to be familiar with this concept. You can take any undergrad textbook, go through it and whatnot. Okay? But it's your responsibility to be somewhat familiar with those concepts, because this class builds on an undergrad class in operating systems. If you have any questions about this aspect, come talk to me at the end of the class. Okay? But I'm not going to enforce that. If you feel that you cannot keep up with it, you can decide before the add drop period that this course is not for you, because that's why I'm going to go through the outline and all of that now. Okay? So that's basically the prereqs. As I said, I don't enforce it. You have to police yourself. If you feel you have the knowledge or you can acquire the knowledge, you can take the class. I don't have any issues one way or another. Okay. The course mailing list I already talked about. We will add, not we, Spire will add you to the list automatically if you're registered. If you're not registered, you won't be on the list until you register. And then I just use that for periodic announcements. Any questions? No questions. Okay, so one final thing is, I have traditionally enforced a no device policy in class, which means that you don't use your laptops or phones or tablets or whatever. If you come to class, you pay attention to what's going on, you don't use your computer. I'm going to enforce that because I find that it is very distracting to most people. Not only whoever is using the laptop, but the 3 people around them are looking at why the person is doing Facebook or some other stuff while in class. Okay, so I'm going to enforce the same, no laptop, no devices to be used during class. If you come to class, silence your phones. Occasionally a phone will go off, as you will see. But be that as it may, try to respect the sort of the class tradition of not using laptops and whatnot and getting distracted by other things. Okay, there's no attendance, so if you feel like that's a better thing to do, you don't even have to come to class. I don't enforce any of that. Okay, but if you come here, you should listen. That's the class policy. Okay, any questions on the syllabus? Okay, everything I said here is also posted on the course syllabus on the class webpage, as you will see. I'll cross-post everything to Moodle as well. Okay, so if you don't have questions, this is a good time to ask before I start talking about an introduction to distributed systems. Questions or comments about the class? Okay. So the class will go better if you ask questions as we go along. Okay, it's okay to not have questions about the syllabus, but if you have any questions, it's good to ask because that's going to result in discussion. It's not a good idea for me to come and talk for an hour, 15 minutes and have nobody say anything in the class. Okay, make it interactive. Yes.
Do we need Linux?
Do you need Linux? You don't need any Linux or any sort. You can certainly program on Mac or Windows. That's not an issue. The only thing I'm going to say is that if you turn in projects that you develop on your favorite platform, language, operating system, the TA needs a way for them to run it and make sure it works. Okay, so I will have some detailed instructions when the labs are given out on what might have to be done. In the worst case, if you use something really obscure, you may have to actually sit down with the TA to show them it works and have them play with your system. Okay? It's not required. It would be good because the EdLab is Linux based. We will give you all accounts on the EdLab. I forgot to mention that. But by no means do you have to actually use it. You can use your laptop to do develop or a desktop to do your development. Okay? So platforms are not necessarily enforced. If you use Java or something like that, that code should work on any platform. It shouldn't matter. Okay. Any other questions? All right, so let's get started. So I'll talk a little bit about what are distributed systems, why are they useful, what are some advantages, disadvantages. We'll also look at some historical perspective on distributed systems today. Okay? So the big thing to keep in mind is most complicated applications, that computing applications that you use today are distributed in some shape or form. Whether it's the World Wide Web, whether you use the Google search engine, whether you use social media applications, you use YouTube, even any application that runs on your smartphone or tablet that uses a server backend is a distributed application. Okay, chat application distributed, email is distributed. So most of the applications that we encounter on a day-to-day basis are networked and distributed. Okay. So it's useful to understand how these systems work, what are the concepts that underlie these systems, how they are built. Okay. That's basically what the course is about. Okay. So course is going to cover basic principles for designing systems of this. Okay. In this class, you're not going to be design a system of the scale of Google, which is a search engine that runs on tens or hundreds or thousands of servers. But you will design systems that may run on a few servers, more than one machine for sure. Okay, so you'll build some distributed application, but not very large ones. Okay, in order to understand the concepts behind it. Okay, so here's the working definition for a distributed system. Okay, so it is essentially a system that uses multiple connected CPUs or machines that work together, that are interconnected using a network. So it's a collection of independent computers that appears to users as a single coherent system, and that one that is also connected over some medium, okay, such as a network. Okay. So typical characteristics of a system are more than one CPU. Typically, each of the CPUs is on an independent machine. Machines are connected over a network of some sort. Okay. So that collection of machines and the software that runs on it is going to be a distributed system as far as we are concerned. Okay. So I'm going to distinguish distributed systems some from parallel systems. Okay. A parallel system is also a collection of CPUs. Okay. Those CPUs are also interconnected. Okay. except that most of the parallel systems, the CPUs are inside one machine. Okay? The interconnection is a system bus or some high-speed interconnect. Okay? In a distributed system, the CPUs, each CPU or some more CPUs are on independent machines, and the network is not a system bus; it's a Ethernet or a WAN, such as the internet. Okay? So there is some distinction between what is called a parallel system, is also referred to as tightly coupled system, from distributed systems which are called loosely coupled. But the boundary is fuzzy, because there are some of the interconnects that parallel systems use resemble a network, a real network of some sort. So I'm going to use a much broader definition, one that actually encompasses parallel system. This is why I said it's a collection of CPUs, not a collection of machines. Okay? So our definition is going to be broad enough to encompass parallel systems, but I want to say that there is a distinction between them. Okay, when you say parallel system, typically people mean it's one machine, it's multi-processors, these processors connected over some sort of high-speed interconnect. And when you mean distributed system, the default picture in mind is these are machines that are interconnected over a network. Okay? But technically, our definition is going to be broad enough for parallel systems to be a special case of a distributed system. Keep that in mind. Okay. Any questions on this? Okay, so this is a very broad definition, and what I'll now talk a little bit is what are some disadvantages and advantages of making your system distributed as opposed to a centralized system. Okay, any program that you write that just runs on one machine, uses just the data that sits on that machine, is what is referred to as a centralized system. It doesn't need resources on another machine. It doesn't need any other machine to run. Okay? As opposed to having a distributed system where you need more than one machine and components of your application are partitioned or distributed across those machines. Okay. So what might be some advantages and disadvantages? The one advantage is that you can share resources across machines in a distributed system. So let's take some examples. So let's assume you have a disk on one machine where you stored some data. Okay. In a distributed system world, another machine can access data on that disk. Okay. So in some sense, you can access storage on other machines. That's an example of resource sharing. Okay. Another example could be you connect a printer to one machine and then you share that printer on your network. Okay. Now a second machine somewhere else can print to that printer even though there is no local printer attached to that machine. That's another example of resource sharing. Here you shared a different kind of resource, which is a printer. Okay. Now you can share all kinds of resources. If you have n machines, you can have n CPUs on those n machines working together. Okay. So in this case, you are actually sharing computational resources or CPU resources so that the application can harness the power of computation on multiple machines. So if you have n CPUs, your application should be able to run n times as fast or scale to n times as many users and whatnot. Okay. So all of that comes under the scenario of resource sharing. Okay. As a result of sharing these resources, you also get what is called a better price performance ratio. Okay. So if you want to build a large server, you have typically two ways to do it. Okay. You buy a single machine that has lots of resources, okay, and you run your application on that one large server, or you can buy lots of smaller servers, okay, and connect them together and partition your application across those smaller servers. Okay. And in either of those two cases, you should be able to service your workload. And the claim that is being made here is doing it in the latter way is more cost effective. Okay. It gives you a better price performance ratio because you can buy cheaper commodity machines but buy lots of them and connect them together, or buying an expensive mainframe or an expensive multi-processor system which can really cost a lot of money. Okay. So building distributed systems using smaller machines, they don't have to be small, but there's just multiple commodity machines, can get you a better price performance ratio. Okay. This is how Google and Facebook and others build their system. They buy really inexpensive machines, but they buy lots and lots of them. Okay, and then connect them together and write their application to run on these machines. They don't go and buy $1 million mainframe or supercomputing nodes to build their application. Okay, that's the other way to build larger applications. Okay, so that's price performance ratio and economics. So you get better economics building systems this way. You're also going to get reliability and scalability. Scalability I already talked about. As you add more machines to your system, okay, you should be able to scale to a higher workload or more number of users because you have more resources, you have more processing power, you have more storage, and so on. So as you have n machine, if you have n machines, as n grows, you should be able to scale. If you design your application well, you should be able to scale with the number of machines. Okay, that's scalability. Okay. Reliability comes to you because you have multiple machines in your system. So if one or some small subset of the machines fail, okay, other machines should be able to take over those tasks and your application should be able to continue to function. Okay. So you can also replicate your data so that if one disk fails, your data is not lost, for example. Okay. So if in your distributed systems, you can have better reliability and you can get better fault tolerance. Okay. So these are all advantages of distributed system. And last but not least, you have potential for incremental growth. Okay. So what that means is when you design your application and deploy it for the first time, you don't need to buy a very large server or large numbers of servers because you don't know whether, let's say you built a new game. Okay, you game developer, you built a game, you put it out there. Okay. You don't know how many users are going to access it. Initially, the game may not be well known, so maybe there are only small numbers of users. It's not very cost effective for you to go purchase a large set of servers and deploy it when there are very few users. Okay, you wasted a lot of resources and they are not being used. So you're better off running your game on one or two small servers. But maybe your game increases in popularity over time and you need more and more server capacity to run your game. Okay. What incremental growth says is as your workload increases gradually, you can add more capacity gradually as well. So if your workload increases, you can buy 4 more machines and you deploy them. And now you can scale for some more time. As your workload or number of users keeps increasing, then they may max out that capacity, you buy some more machines and so on. So you can scale gradually over time. You don't need to buy all of your resources upfront. If you design your systems well, they will allow you these kinds of benefits, okay, which you may not get in a centralized system. You have to decide what is your peak workload and provision for that. Okay, questions about this? Okay, so what might be some disadvantages of distributed systems? So these are all good advantages, but of course there are some disadvantages as well. First is your system is distributed and inherently more complex. You have to write these applications that run on these systems, and writing a distributed application is somewhat more complicated than writing a simple application that runs on one machine. Okay, so designing application design becomes more complex. You need operating systems, programming languages, and runtime systems that will support distributed applications. Okay, so those will also need to be more complex. They will need to support more features so that your application itself can be distributed. Okay. Okay, that's one disadvantage. Okay. Second one is network connectivity is essential for your distributed application to run. If the network goes down, okay, unless you have redundant networks, okay, you may have redundant machines, but often you may not have redundant networks. So if a network goes down, that's the interconnect. Your application is going to go down. Okay. So network connectivity is essential for functioning of your distributed application. And the third, that not the least important disadvantage is that this raises number of security and privacy concerns. Okay? Because you put out your applications on a network, other clients' machines can access it, and so can malicious users. Okay? So your applications, distributed applications, are more vulnerable to malicious attacks by hackers. There are privacy issues if you put sensitive data and your hackers access your machine and steal the data, then you sort of violated privacy of your customers or users and so on. So all of these aspects become more important to think about upfront. Okay? Often when you design your distributed application, you don't think of security, you just build it so that it works, and security is often an afterthought, which basically means that there are all sorts of problems lurking around which allow unauthorized use of the machine and unauthorized access to the machine, become vulnerable to hacking and so on. Okay? So designing your systems in a secure way is just as important as designing them to scale well or designing them to be reliable and handle faults and whatnot. Okay? That's an important aspect that we have to keep in mind. And I emphasize that here because security is a topic that I'm going to gloss over more or less, because that's a topic for an entire graduate level class. As I said, we'll talk about it very briefly. But that's not to say it's not important. It's just that it's an important topic that's important enough to cover in its own class. Okay. So those are some pros and cons of designing your systems in a distributed manner. All right. So the next thing we are going to talk about is what is referred to as transparency in distributed systems. This is an aspect of how you design your application. Okay? And what this essentially means is there are many aspects in your system design, and the question is, what are you going to expose your application? What is your application going to expose to its end user, and what is it going to hide from the end user? Okay? And the idea is the more you hide from the end users and make it transparent, the more convenient our application becomes for the end user, but there's more complexity underneath because the system has to deal with that complexity. And I'm going to give you an example. There are many dimensions of transparency, as you'll see. In fact, there are 8 or 9. I'm not going to run through all of them. We'll come back to these as we go along in this course, but just to explain to you what this even means, I'm going to take an example. So let's look at replication transparency. Okay? What replication transparency means is that if your system is replication transparent, it's going to hide the fact that the application runs on multiple servers from the end user. End users will not know that the machine is actually, the application underneath actually runs on multiple servers. Okay, so now let's take some real examples and try to understand how this is done. Okay, so I'm going to start with Google, that all of you are familiar with. Okay? So Google's interface is you go to google.com and it pops up a box where you can type a search query. Okay? You just put in whatever search query you want and then you say submit, and it goes, processes your query and shows you some results. Okay? Now, nowhere in this interface when the user is interacting with Google has Google exposed to you that the search engine is running on multiple machines. In fact, it runs on tens of thousands of machines. You don't know that this is happening under the hood. Okay? There are lots and lots of users accessing Google at the same time. Google search engine has taken responsibility for figuring out when a query comes in, which of these thousands of machines is going to process it for you. Okay, so many different users are going to, queries are going to be sent to different machines. You don't see that happening under the hood. Okay? All of that is hidden from the user, so you get a very easy, convenient to use interface to use Google. Okay? Another way to have designed it would have to be expose replication to end users. In other words, not make the system replication transparent. Okay? So in this case, you, the user, is responsible for not connecting to Google as a search engine, but a specific replica of the Google search engine. So it could be machine 110. Okay? So you have to connect to that specific machine and send your search query directly to that machine, and different users may be assigned different machines. Okay? So now, in such a world, your system is not making the replication transparent, it is actually exposing the fact that there are many replicas, and it's requiring users to deal with the complexity of figuring out where is the closest replica that I can connect to, which one is going to give me the fastest response, or which replica should I use at all, even if I don't care about any of these issues. Okay? That's another way to design your system. You're exposing a lot of the underlying architectural details to the end user. Okay? So as you can see, in this case, keeping the fact that there are replicas transparent from the users yields to a better user experience. Users don't have to care about all of that complexity. They just want to send a search query and get result. They don't want to worry about which machine and all of that. They want to go on, actually look at what they're searching for, not have to deal with these complexities. Okay? So these design decisions can have very important implications on the usability of your system. Okay? What you will hide from your end users and what you will expose matters. Okay? And that is what transparency means. It doesn't mean that always everything should be hidden from users. In some cases, exposing certain functions is actually important or desirable. But in other cases, exposing it is a limitation. It can actually hurt usability. Yes,
are there any examples, real-time examples, where it's not transparent?
Okay, question is, are there examples where it's not transparent? So there will be many things here that you will actually have to think about. Okay, so migration is one example. So if your application is running on one machine, okay, the system decides for whatever reason is going to move that to another machine. Should you hide that from the user or not? In some cases, probably not, because if I need to get to my files, if I don't even know what machine it's at, then I cannot get to it at a later point. But if I am accessing a service, if it's a web server, why does it matter? I just need to know the name of the web server. So it answers is going to depend. Okay? You have to carefully think about what you're trying to do. Okay? And does the user need to know or be involved in this decision? Okay? The more the answer is no, the better you are, better off you are keeping it transparent. Now that's an abstract answer. The real answer is going to depend on what's the application, what are you trying to do. Okay. Any questions here? So there are many dimensions. Okay, I didn't go through all of them. Okay, I'm just going to quickly look at them or mention them rather, and we won't discuss them in detail. So location transparency hides the location of where the resource is. Okay, it could be the location of the server or the location of your file. You simply have an handle rather than the actual physical location. Okay? Most web servers, you basically use a name, www.umass.edu. Okay, you neither know the actual IP address nor do you know the physical location where the machine is. Okay? That's an example of location transparency. The migration I just talked about. Relocation is the same, very similar to migration. If for whatever reason your system is moving data around, moving applications around to either balance the load or to handle failures and so on, how much of that is actually hidden from the end user and how much of that is exposed to the end users. Okay. Concurrency basically says the fact that a resource is shared concurrently by multiple users is hidden from the end user. Okay. If there are locking to be performed, the system is going to acquire the lock for you. The user doesn't have to be aware that some other user is also accessing it, so I should actually try to get a lock before let other users access it. So synchronization is handled under the hoods for you. Okay. Failure transparency is actually a scenario where it's better to keep failures transparent. Okay. So if you're connected to a system, some component of the system fails, and it transparently fails over to another redundant resource, this is all good from the end user's perspective. End user doesn't have to see a message saying server not responding, retry or anything like that. System is dealing with it automatically for you under the hoods. Okay? That's failure transparency. Okay? Persistence basically says it hides the fact that whether the resource is on memory or disk. This is often not a very important dimension. Okay? Typically, if you put data into a system, you expect to get back that data if it's a cloud system or so on. So in most cases, systems are persistent. Okay? So you don't need to actually worry much about it. But it is another dimension. Okay? So there are many such dimensions. And as we go along and we talk about some of these topics in more detail, we will come back to this. Okay? All you want to keep in mind at this point of time is when you design your distributed application, there are important decisions to be made as to what you are going to hide from your end user, what interface you provide, how much complexity is under the hoods that you are going to deal with on behalf of the user. Okay? And keep in mind that the more transparent you make the system along these dimensions, the more complex your underlying system becomes. Okay? Because now you meaning the application developer, is dealing with all of those issues on behalf of the user. Okay? So there is also a simplicity complexity argument. It may be good to hide things from the user, but then it's going to make your design more difficult. In some cases, you may not want to do it. You may say, I don't really want to do this. Let the user deal with it, even if there is an inconvenience. So these are all decisions to be made. Yeah, so that's the part you should keep in mind at this point.
Can you differentiate between migration and relocation transparency?
Okay, the question is, can you differentiate between relocation and migration? They are actually not very different, except that what relocation says is it's a form of migration where the resource is actually moving while the resource is in use. So it's what is referred to as live migration. Okay, so migration can be online or offline. When we talk about things like virtual machines, we'll come back to this. So if you are moving the resource while it's in use and it doesn't even know things have been moving under the hood, that's called relocation transfer. Migration here means an offline case where essentially the application or the users are not accessing the system, things move, you restart, does the user know things have moved or not? So that's the
So in
distinction.
case we hit our site and we get 304 like move, it would be in the relocation.
Okay, so you are asking, so the question is, if you access a web page and you get an error code that says the resource has moved, is that a relocation or migration? So that's a scenario where the moving is not transparent. It's not a because it's actually telling you it has moved. I don't know where it is. I can't give you access to it. Okay, so that's an example of not making it migration transparent. Okay. But it's not just web pages or data moving. We'll see that lots of resources can move. It could be processes, there could be virtual machines, and so on. Any other questions? Okay. So I'll briefly talk about open distributed systems. We are not going to deal with it a whole lot in this class, but it's still an important topic. So what an open distributed system is basically that the interface that the system exposes is well documented, it's openly available so that other systems can be written to interoperate with the system. Okay? So systems could be what are called closed or open. In a closed system, the APIs to the system are not published. You're not allowed to access those API. The system design may not be documented in an open form. Typically, in this case, the developer or the company that built it doesn't intend for other applications and other system to interact with the system in any way. That's an example of a closed system. As opposed to having a system open is one where the server publishes an API. Okay? You can use that API and build other things on top. Okay? And just to give you one example, Google Maps API is an open API. Okay? So the Google Maps service exposes API and interface whereby you can use the Google Maps interface and embed maps in other applications or make a request to map to give you directions using other applications and so on. You don't explicitly need to be accessing Google Maps in order to use the mapping data or mapping service. So you can use, when you have open systems, you can use the interface, you can use the data that the system exposes in other applications, and this interoperability allows you to build richer services and whatnot. Okay, so there are many benefits to it, which is interoperability, portability, and last but not least, extensible. Okay, when systems are open, they can add new functionality over time. Those functionality can be exposed, others can use it, and so on. Okay? So building your system to be open in some shape or form is a good thing. Okay? And many web services that you see today, they expose some form of interfaces. They're open to varying degrees. Okay? Open could mean everything from the code is available and the interface is known to the interface is documented but the code has not been released to nothing is actually accessible, neither the code too. So there is a whole spectrum of what open means. And by and large, systems today at least expose APIs that allow you to use those APIs to do other things, whether it's a weather service that allows you to make a query to find out the temperature at a certain location, or it's a social media application that allows you to go make a query. Facebook has an open API that allows you to make queries on the Facebook data and so on. So there are many services that at least expose APIs, and many others are even open in that the code is also available so that you can go modify the code itself. Okay, so keep that in mind as we go along, because as you build your lab, you will have to document your interfaces, think about how to use them for other parts of the lab and so on. Okay, so we will not necessarily make your system open, but some of these principles will apply. Okay, so I'm going to talk a little bit about scalability now, just so that you understand again some of the benefits of distributed systems. So what the slide shows is essentially with sort of different flavors of what distributed means. Okay, so you can have centralized services where there's a single server for all the users. You can have centralized data where the data for your service is on one machine, but the code for the application may be running on multiple machines. Or you can have centralized or distributed algorithm where the code and the data itself can be distributed. Okay? So when you say distributed, its question is what aspect of your system is distributed. Is the code distributed? Is the data distributed? Or both of those distributed? Okay. There may be scenarios where the data resides on one machine, but the application runs on multiple machines and accesses that centralized data. There may be scenarios where the data is itself replicated or distributed, and you can have the code also distributed. Okay. So you get different permutations. Okay. And then you have pure centralized where the algorithms are centralized, the code is centralized, and the data is centralized. The reason I'm mentioning this is many times you may decide that you need to scale capacity and you may run your application on multiple machines. But all of the application accesses the data, a single copy of the data, and that data is not centralized, and that may become a bottleneck. Okay? So to be truly distributed, you need both your code and your data to be replicable, distributed, and scalable. Okay? But that is going to give you a design point where you have to deal with lots of other issues like consistency and replication and so on. Okay? So when you design your system, you have to decide what is it that you want to distribute in your system. Is your algorithm distributed but the data is not, or do you also need your data to be replicated? In which case you will have to deal with consistency and so on. And depending on what design decisions you make, there are going to be scalability implications. That's basically what this slide is saying. You will basically have different kinds of bottlenecks. Either your server or CPU is going to be a bottleneck, or your disk is going to be a bottleneck, okay, depending on what aspects are distributed or not distributed. So when you go and start thinking about your labs and so on in a subsequent class, all of these issues you should think about. How are you going to design your system? And we'll come back to some of these issues as we go along. Okay, so just to follow up on the previous slide, here are some techniques to scale your performance of your application. Okay, so these are principles for designing what are referred to as distributed or decentralized algorithms. Okay. Some of this may not make complete sense as of now because we haven't gone into the details, but I'm going to mention them anyway. So no machine has complete state. Okay, that means that the state is not a bottleneck. State is any data that you may have to keep in memory for processing the application. Okay, you can make a decision based on local rather than global information. Okay. A single failure should not bring down your system, and there is no global clock. Okay. If you have these four properties, you have a good decentralized or distributed algorithm. Okay. I'm going to mention what these are very briefly. We'll come back to them. Okay. So no machine has complete state essentially means that the state of your system or whatever application state is distributed across multiple machines. So a single machine is no longer a bottleneck because the state is going to grow as you have more and more users. If all of the state is centralized, that's going to be a limitation in terms of scale. So distributing your state gives you good scaling properties. Okay. If you have to make a decision when a request comes in order to process that request, if you have to make some decision where you only use local information, that's going to give you better scaling than if you need to go interact with several other machines in order to reply. Okay, because the more interactions there are, the more complex your system is and more are going to be the scalability implication. So making decisions based on local information is going to give you the best scaling property. That's not going to be always feasible. Because to process a request, you may need to go access data or request services from other machines. But the less you do this, the more scalable your system is going to be. Okay. Clearly, the third property is a good one where failure of any one machine should not bring down your whole system. What that means is every aspect of your system needs to be replicated. There should not be what is called a central point or a single point of failure in your system. Okay. Every aspect of your system needs to be replicated. This includes even keeping username and password. If you think I replicated everything in my system, but all my login information from one of my users to access this web service is on one machine, that machine goes down, you can't, no user can even log in. even though the rest of the system is accessible. Okay. So there should not be a single point of failure. Every aspect needs to be distributed or replicated so that any failure is not going to take down the whole system. Okay. This no global clock is not very easy to explain without a lot more detail, but all that is saying is you shouldn't rely on machines being tightly clock synchronized in order for your application to function correctly. Okay. A global clock basically means that there is one one machine that can give you the authoritative time, and all machines are tightly synchronized to that one machine. Okay. The less you have to make this assumption, the better off you will be. There will be lots of scenarios, as you will see in your labs and so on, where you have to rely on things like timestamps. Okay. Timestamps often mean you are relying on a global clock, because if you compare timestamps across machines, they are meaningless if the clocks are not synchronized. If the clocks are out of sync, comparing a timestamp here and a timestamp there and trying to reason about it doesn't have any meaning unless the clocks are synchronized. But when you require clocks to be synchronized, it gets us into all sorts of problems, as we will see, because you need tight synchronization for certain things to work correctly. Okay. So the no global clock property we will come back to. Okay. Just keep that in mind, that it has to deal with clock synchronization, and any application that relies on tight clock synchronization is going to have some issue or the other, as we will see. Okay. So those are all good assumptions to make in order to design your system well. Okay. And there are some techniques that are often used. Again, we'll come back to these techniques and look at them all in quite a bit of detail. Okay, first one is asynchronous communication, which always scales better than using what is called blocking or synchronous communication. When we talk about communication in distributed systems, we'll come back to this. Okay, and then there is distribution, which is essentially has to deal with caching and replication. And we'll see that replication is a common property that is used in distributed system. One way to do this is also to employ caching-based systems, where you cache copies of the data on other machines and use this cached copies to optimize performance. Okay. Yes?
When you need so much replication, will the memory or the size of the system not be a problem? You'll be replicating everything.
Okay, question is, when you have to replicate everything, does that not increase the overheads on your system? Okay. So it is indeed the case that if you have to replicate everything, there is going to be higher complexity and higher overhead. That's what I said was a limitation of distributed system. Okay, so you have to really weigh what are the end goals for your application. Okay, what is it that you're willing to tolerate, and what are some scalability properties you want to achieve. If you want your system to scale arbitrarily, okay, you have no choice but to assume that you replicate everything. If you want to achieve certain more limited scaling properties, you don't have to replicate everything. This is going to be an important design decision. All I said here is the less restrictions you put on what you don't replicate and so on, the better you're going to scale. But the flip side of it is the more replication you do, more complexity you have. There's consistency, maintenance, dealing with replicas, dealing with failures. All of these also have to be dealt with. It makes your system more complicated. That is for sure. Okay, so we have a little bit of time. So I'm going to go quickly through some history of how distributed systems have evolved. Okay, so we'll start with early models for distributed systems, and we'll end with what kinds of systems you see in practice today, okay, which are distributed. Okay. So early distributed systems used to be based on what are called mini computer models, where, so this was back in the 60s and 70s, 40, 50 years ago, where there were the very first distributed systems were built. Okay? So in those days, you had your sort of machines you could buy were either mainframes, okay, which cost a lot of money, or what were called mini computers. Okay? This is pre-PC era. There's no concept of a personal computer. Okay? So what you had was this mini computer. You had these dumb terminals that you connected to the mini computers, and then multiple users would each get a terminal. They would connect to this machine. They would log into the machine and submit jobs and whatnot. And these computers had the ability to connect to other machines. Okay? Often using a dial-up telephone line. There's no concept of the internet either in those days, the very early days. So to connect to another machine and send it some message, you literally had to, it was almost like making a phone call where one machine had to dial the number of the other machine, the modem on the other machine would pick up, then they would establish a connection, and then once the connection is established, the two machines could talk to one another. And users on one machine could send data or send application requests to users on other machines. This is basically how very early distributed systems were built, very rudimentary systems. Okay? Each user had local machine. Most of the processing was local because remote communication was cumbersome, it was slow. Dial-ups, telephone lines are not the fastest networks you can have. So you could fetch remote data or send remote data, but still very rudimentary, lot of processing still local. Okay? Uh, Now, maybe a decade later, prices of hardware dropped to a point where workstations became feasible. Workstations were essentially very early forms of personal computers, but workstations had more powerful capabilities. Okay, they were sort of stripped down versions of mini computer. But what this allowed you to do was to give each user their own machine. Yeah, so you have an environment where each user has their workstation, the workstations are all networked. So that resulted in a new class of distributed systems where the workstations were still expensive. Okay? Buying one workstation would cost maybe 10, 20, $30,000 and not a $300 machine. These workstations were still significantly expensive. So now if you had 10 of them, you could say, how do I actually use the resources on all 10 in a cost-effective manner? Okay? So this resulted in all sorts of distributed systems where you could submit a job to one machine. If that machine was overloaded, that machine would talk to some other machines and see which machines were underloaded and have this other machine execute the job for you. Okay? And thereby using resources on underloaded machines. Overloaded machines could sort of send jobs over to underloaded machines and use resources on all of the machines in your system. So some of these ideas still live on, as we will see. These are batch schedulers where you submit jobs and jobs get executed on any available machine in the system. And these were sort of the early systems that where these ideas arose. We will talk about a system called Sprite that was built in the 80s and System V, which was also built in the 80s, that was based on this workstation model of distributed computing. Okay. So from the workstation model, essentially arose the client-server model, which is there with us even today. So in the client-server model, the distributed application runs on two types of machines, a client machine and a server machine. The server machine is assumed to be more powerful, more resource capable than the client machine, and it offers a service. Okay? And the way the client machine accesses is they send request to the server, server processes the request, sends back a reply. And that's your standard client-server model. Client-server offers a service. Service is basically requested by the client using request. And all client-server systems work the same. Okay? Web is a good example where the client is a browser, the server is a web server. The browser makes request to web server, the web server sends back replies to you, to the browser. Okay, so that's the client-server model. It is widely used in a variety of scenarios, file servers, database servers, print servers, web servers, all kinds of servers use this kind of model for communication. Okay. We will distinguish the client-server model from what is referred to as a peer-to-peer model, where we don't distinguish between the type of the machine. In the client-server model, your clients and your servers. The peer-to-peer model, all machines are assumed to be equal. A machine can either be a client to another machine or a server for another, so be a server for another machine or act as a client to that accesses a different server. So you see how peer-to-peer models have also arisen independent of this, and will distinguish them from the client-server model. But by and large, the client-server models are the ones that are still very popular today. Okay. So now, if you go down the evolution path, from the client-server model arose what is referred to as a processor pool model. Okay. In a processor pool model, you have a server with lots of processors, or it could be smaller machines. Okay. But you have a pool of CPUs that are sitting somewhere in a closet or in the machine room somewhere. Okay. Users will submit, assume to submit jobs to the processor pool, and the or run applications. And the one processor on the processor pool is assigned the task of executing this task or executing the job or the application. Okay. So, in other words, a server is now a pool of processors, pool of CPUs, not a single CPU. It's a pool of CPUs. There are many clients or many users, and they're submitting jobs or they're starting up application. And the system will assign one processor from your pool to each job or end user. Okay? And that's referred to as a processor pool model. It arose again 15, 20 years ago, but it lives on today. Okay? If you have a large cluster, okay, that is essentially a pool of processors. You can submit a job to a cluster. The scheduler will then assign some machine to this job to some machine, and that processor will execute your job for you. Okay? So the similar idea lives on, but this sort of arose again 20 years ago, and it was referred to as what is called the processor pool model. Okay? So we are still in the late 80s, early 90s, and this is sort of the historical evolution of distributed system. And now we'll look at a little more modern system. So here are basically more modern trends in what distributed systems do these days. So I talked about clusters already. So from the processor pool, you have cluster computing, where you have lots of servers that you bought. They're sitting on a rack or lots of racks. You submit jobs. The scheduler assigns some machine to run the job runs, results come back, and then process continues. Other jobs are sent to the machine and so on. Okay, that's called cluster computing. Okay. It's also related to this notion of data centers, where data centers are essentially facilities that actually house more than one clusters that perform these tasks. Okay. There are lots of different kinds of systems that allow you to implement cluster computing systems. I'm not going to go into them now. We'll come back to them. Okay. A related concept to cluster computing is what is called grid computing. Okay. Grid computing allows you to take each of these clusters, okay, and then interconnect them over a WAN so that they also interoperate. So if you run a cluster and some other person at some other institution runs a cluster, you can use grid computing techniques to interconnect them. So when you submit jobs to one cluster, if this cluster is overloaded, it can other cluster has available resources or cycles, it can send your jobs to this other cluster and vice versa. Okay, so grid computing is very related to cluster computing, where you have middleware software that runs on the clusters that allow clusters to be interconnected. They are what is referred to as federated. Okay? In that context, we'll look at what is also called as volunteer computing, using applications like SETI at home and whatnot. We'll come back to that as well. Okay. Now, what you see today are sort of these last three bullets. These are WAN-based clusters or distributed data centers. Examples of these are all modern large distributed systems are based on this model. Google is a good example. Okay. The application is not even limited to one cluster. It is a global application that runs on many different clusters on many different data centers across the world. Okay, the Google search engine is distributed in many, many countries across the world. Okay, so you have very large-scale distributed systems that run on lots of machines that are organized as clusters. The clusters are interconnected over WAN links in the internet. Okay. So related topics to those are virtualization and cloud computing. Cloud computing is a similar model where you can actually go rent resources from a provider. Resources could be one machine, it could be a cluster of machines, and so on. Resources are often given to you as virtual machines rather than physical machines, and you can run whatever job you want on your machine and relinquish the resources when you are done. Okay. So cloud computing essentially is a model where you can rent rather than buy resources. Okay. You can lease them on the fly, you can relinquish them on the fly. And we will come back to cloud computing concepts and virtualization concepts for that matter and look at them in quite some detail. Okay. But you will see that there has been a gradual evolution of distributed systems to be bigger, more scalable, and ever more distributed. You go from one cluster to multiple internet connected clusters to really global spanning clusters. that will run very large scale applications. So systems have continued to evolve, and they continue to evolve even now. And then so what you see today are things like cloud computing. And there are many emerging models where you may not even think of the system as being distributed in some shape or form, but it is an example of a distributed system. One example is what we call distributed pervasive system. Okay, so this is basically tiny embedded nodes which have a small CPU and a small amount of memory that is performing some task. It may have a sensor on it. The sensor performs some task. The node is going to send your data to some central site which is going to process it. Okay? So you have all kinds of computing now being embedded into the environment. All of these nodes are networked. They can send data to other machines and be part of a larger distributed system. Okay? And so this basically, the reason this is now feasible is the cost of computing has fallen to such a level that you can build these tiny nodes for a few dollars. Okay? You can buy a tiny microcontroller or CPU for a few dollars. So it becomes feasible to embed computing in any other device that's not even a computer to begin with. Okay? So your car is now a distributed system because it has lots of microcontrollers. They're connected via LAN. It may have lots of capabilities to talk to other systems for safety purposes and so on. Okay, you don't think of your car as a computing system, but it is in some shape or form. Okay? If you take a typical building, you will see that also is an example of a distributed system because it has embedded sensors that are sensing what is going on. The sensors send data to centralized servers. They control variety of functions. So example being lighting. There are sensors. There's a sensor in the back there that senses when nobody is in the room. Okay, it will basically send a signal and turn the lights off. Okay, that sensor can also signal a system that controls the air conditioning in the room, and if there is nobody in the room, it will not cool the room anymore and waste energy. Okay. This is an example of a distributed system because there are sensors, they have computing, they have networking capability, they talk to other machines. Okay. Now you don't think of these as distributed systems, but they are in some shape or form. Okay, you have your satellite cable TV box. Okay, full-fledged computing inside. Okay, typically it runs an embedded form of Linux. Okay. You don't think of your TV. There are smart TVs coming out that also run embedded operating systems. Okay. They have computing capabilities, they have networking capabilities. They can often stream from Netflix or YouTube or Hulu or all of these services. Okay. It's an example of a distributed application. So what this is saying is distributed computing has evolved to a point where computing is now embedded in other devices that are not traditional computing devices, and then those devices become networked, and those devices can talk to other services, other machines on the internet, and is part of a distributed system. Okay? You can even buy appliances now that are called smart appliances. You can buy a washing machine that you can control with a phone. Okay? Why you would want to do it is a different problem, but you can buy these things and they do have network capability. They are on the internet and you can control it. So it has computing on board and whatnot. Okay, so there are all sorts of devices like this. So I have this device here. This is a pedometer. It computes or not compute. It tracks how many steps you walk every day. Okay? It has Bluetooth capability. It's tiny microcontroller. It's a Bluetooth capability and uploads this data to the internet every day. So I can go to a website and see how much walking exercise or running exercise you get. Okay? This is another example of a health-based distributed application, which is basically driven by sensor. Now you can't think of this as a computing device, but it is. It's a small computing device that is built into this. Okay? So distributed systems are becoming more pervasive. So they are no longer client server laptops. Your phone is a computing device, a tablet is a computing device, car is a computing device. So you see all of this computing everywhere. So towards the end of this class, we'll come back to pervasive system and we'll look at this whole concept of designing sensors and devices that can provide you some nice service that is not a traditional computing service like Facebook or things like that. Okay, but all fall under the realm of distributed systems and distributed computing. Okay. Any questions on this? Okay, so I have 5 minutes. I'm going to quickly run through some operating system concepts. There are only 3 slides here, and then we will end for today. That will be the end of the first lecture. Okay, so I presume all of you are aware of what an operating system is. I don't need to define that. Okay, so on OS, this is undergraduate textbook definition. An operating system is essentially a resource manager or an arbitrator that sits between the underlying hardware, okay, and the end user. So it's a piece of software that sits between that runs on your machine, that sits between the underlying hardware and the end user, and it provides an easier to use abstraction to your end users. Users don't need to deal with where on disk should you store your file. You just create a file, the OS decides where to put it on disk. Users don't need to deal with when you start an application how much memory to allocate to that application. OS is going to deal with it for you. Okay? So lots of underlying details of dealing with hardware resources are dealt by the operating system for you. So in that sense, it's a resource manager or an arbitrator that is going to sit between the end user and the underlying hardware and provide an easier to use logical machine abstraction to end users. Yeah. There are many different operating systems. You probably know Unix, Windows, Mac OS, Linux. They are all forms. Early versions of all of these operating systems were all uniprocessor operating systems. By uniprocessor, what we mean is they were designed to run on single CPU machines. Okay? Now, any machine you look at today, by default will be multi-core. Even your phones have 4 cores, and your any computer that you buy will have multiple cores. So all of these operating systems have transitioned from being uniprocessor operating system to multiprocessor operating systems. Okay? So this is still an example of a uniprocessor operating system where we have what is referred to as a microkernel architecture. This is a way to design a uniprocessor operating system where the OS kernel is a very small core called a microkernel. Okay? And lots of the functionality that you typically put inside the operating system kernel are pulled out and run as user level application. So your file system is an application that runs in user space. Your memory manager is an application that runs in user space. CPU scheduler is an application that runs in user space. The microkernel is a very compact kernel that is just going to enable all of these OS components to interact with one another. Okay? This is a way to design operating system where rather than putting all the OS functionality into one kernel or one system layer, you essentially have made it more modular. You pulled out some of those functions and made them their own system daemons or system processes that allow you to interoperate. Okay? So there are many reasons why this is a good thing and a bad thing. Okay? The good part of this is it's highly modular. You can make changes to the file system without knowing what the CPU scheduler does or what the memory manager does, because this is its own code base. Okay? So it's very modular, portable, and whatnot. The disadvantage of microkernels is that there is a high performance impact between as a result of this modularity, where these modules have to interact with one another and using inter-process communication, and that's a high overhead. Okay? There is much higher cost to interacting across processes than interacting inside a machine, inside a system. Okay? I'm going to come back to this because we've run out of time and talk about this and the last 2 slides next time. Okay, so we'll stop here for today. If you have any questions about enrolling in this class and you're not registered, come see me now. Otherwise, I'm going to see you all next week, okay? Next Monday.